Okay, ladies and gentlemen, let's go ahead and finish up some of our discussions on series. Now, last example that we just did, we talked about expanding a natural log. And by expanding natural log, we equated the coefficients and the derivatives of the natural log, and we expanded around x equals 1. And by expanding around x equals 1, made a significant difference in comparison to expanding around x equals 0. With x equals 0, we just had simple, straight up individual terms that were monomial terms. And we plugged in 0. But by expanding around 1, we ended up with x minus 1 as a term, x minus 1 squared as a term, x minus 1 cubed as a term, x minus 1 to the fourth as a term. And we had to, when we equated derivatives, plug 1s in to our derivatives, solve for our coefficients. So we got to that. That brings us to a Taylor series. And in fact, this last example already was a Taylor series, because if, again, we look, we have some function with respect to some other constant that we're expanding around, okay? You don't have the initial term because of the property of natural log. So the general form would be the coefficient c sub 0 is going to be f of whatever number you're going around. So if I'm expanding around x equals 2, it would be f of 2. If I were expanding around the number 3, I wanted it to match at 3 and expand from there, I would say f of 3. But in the end, you have the generic form, which is f of a, whatever you're expanding around, plus the next term is f prime of a, then f double prime of a over 2 factorial, f triple prime of a over 3 factorial, for the reason we talked about in the previous videos. And it's x minus a to the 0, x minus a to the 1, x minus a squared, x minus a cubed. That is called a Taylor expansion. Now, if instead of a Taylor expansion around some number, we just expand around 0, well, that simplifies everything tremendously. Now we go back to simply having regular x's, a's, etc. So in this case, we end up with not a here. I miswrote this. This would be x's because those are your variables because it's f of x. So you can go ahead and expand around 0. Now, so a maclaurin is nothing but a Taylor expanded around 0 rather than a. In our example number 1, let's take sine x. And I will put this online, but we know some basic standard series. Those basic standard series are right here. So it should be online, or if you wish to, you can pause the video and use your digital device to take a picture of that. But we have standard series that have been built up because they're ones that we used often enough to memorize. With that, I want to find the sine of 3x squared rather than just sine x. So to find the sine of 3x squared, I'm going to use the standard form of sine x, write out the standard form right from our standard forms, except now I'm going to substitute 3x, the quantity squared, in everywhere I see x. So instead of x minus 1 over 3 factorial x cubed, it's 3x squared minus 1 over 3 factorial 3x squared cubed, and substitute it in. Down here is one we've already done in a power series. We say 1 over 1 plus x cubed. That is very similar to 1 over 1 minus x. So we have to find u. Once we find u, we can substitute u in to the problem, and instead of 1 over 1 minus x, it's 1 over 1 minus negative x cubed. Plug it into the summation, which allows us to plug it into the actual series. Why in the world are we doing all that? Because if I want to integrate this right here from 0 to x, t cosine t to the 5th dt, that is non-integrable according to everything we know at this point. So what we're really going to have to do is use one of our known power series and adapt it with a substitution and use a power to expand into something that's a polynomial, where polynomials, of course, we can integrate and differentiate with relative ease.